Okay, so let's now move to, let's say, we have this theory or these ideas provided by the theory, and then we now want to test them in a real experiment. I hope that I convinced you that, going to the accelerator, okay, is trivial, but is a nice place to go, because rather than, waiting for the sky, where you may see also effects that are difficult to explain, why in this case, you can, in principle, disentangle different effects, as we do for particle physics. This was, the way how we learn a lot about the standard model. So again, that makes sense, in my opinion, to try to apply the same methodology also for the dark matter searches. So what we need, based on what we mentioned before, is, again, place where you have an A prime produced. That you can do that mainly in two ways, either in a fixed target experiment, where you throw your beam through a material, and then again you produce gammas, and these gammas produce A primes, and then you spot in some way the effect of the A prime. Or you do a collider, for instance, Z plus Z minus, but nothing prevented to have, proton-proton or whatever colliders you may think about. Or same thing also for the fixed target using proton beams. It's, absolutely good. Maybe, you may have other processes, in particular producing a lot of mesons, because protons have more hadronic interactions, and then you produce a lot of mesons, and mesons again decay by zero decays in gammas, and then you have a gamma-rich environment where you, in principle, can produce the A prime and spot the effect of the A prime. There are, advantages and disadvantages in fixed target versus colliders. Colliders usually is a, cleaner environment, because you know exactly what you are colliding, and what materials, you have side effects. Throwing your beam through a material produce, for instance, radiation or other particles. It's more complicated. On the other hand, in a piece of material, you have 6 to 10 to the 23 particles, while to have the same intensity with two beams is much, much harder. So, again, depending on what you want, a high intensity or higher, let's say, cleanness, less background, you go in the different areas. There are advantages and disadvantages in the two approaches, and also the energy. You can, in collider, you have head-to-head interaction where you exploit the entire energy to produce something. In case of a fixed target, part of the energy is just lost in the boost that you give to the particle you produce. So again, it's less available in the center of mass, okay? So this is, general concept that apply also for dark matter searches. In particular for fixed target, since again, we are a JLab, we are, mainly reviewing experiments here at Jefferson Lab. Fixed target, there are different approaches that I will show you more in detail, but just are sketched here. Beam dump, for instance, you throw your beam through a, massive material, you produce stuff, and then you shield the standard model particle, and you have a detector downstream that can only measure particles that are weakly interacting, flabily interacting. There's different languages, flabily interacting particle. FIP is the ones that they use at CERN, for instance, to indicate that these particles. We say, weakly interacting particle like neutrinos. This is exactly the same technique that you use to measure neutrino oscillation, DUNE or big experiment, mini boon, other experiment at Fermilab. Missing momentum is, again, tricky because you throw your beam on a target and you simply see the disappearance of something. Because if the particle has a weak interaction, you're expecting it to escape your detection. Okay, so you throw it and you are expecting to see the whole energy that you throw in, and you see a missing energy. So maybe you are producing something that escapes your detector. If you are sure that your detector is, the efficiency of your detector is well under control, then you can say, I produce something that, fly away, that didn't interact as I'm expecting. Even better if you do the same thing, but measuring the momentum rather than the energy. It's even more precise. I'm expecting, to see some momentum in a certain direction, and I see a particle that goes in a different direction and say, okay, maybe it lost some of this momentum, was lost along the way, producing another particle that I'm not detecting. Very similar as neutrinos, anti-neutrino in proton decay. Okay, you don't measure the anti-neutrino, but you see that there is a missing energy associated to the detection of proton and the electron. Exactly the same concept, same idea. Or you may focus on looking at effect, like for instance, assuming that you produce a force carrier, it is A prime, in our case, it is a heavy photon or dark photon. It may decay in E plus E minus, and so if I measure a pairs of E plus E minus and try to, do invariant mass, I'm expecting to see a peak, a bump, because it comes from the same particle. As you know, a particle decay in two bodies has, a sharper relationship between the mass and the decay product. Okay, so there are many different, or other, more complicated. You can think that dark matter, when it is produced, gets excited, and then when you spot it, you see the effect of decaying dark matter. That again, these are all trying to duplicate and mimic what happens in for our standard model world, where you may have all this kind of effect with standard model particle. We just apply the same, idea, the same reasoning to dark matter, same concept. And again, this was what people did actually. So JLab or mines, where they had electron beams, you produce A prime, and then you measure the pairs of E plus E minus, and check if the pairs E plus E minus resonate in a bump. Very simple, very trivial, let's say. Or you do the same in fixed target with a proton beam, Na48 at CERN, for instance, where you produce, here in this case, you mainly produce mesons, and then you see, because again, we want to look for the dark photon, you need a photon, start from a photon. So you need to have pi zero, etas, or particles that likely decays in gammas. And then you have, in this case, you produce a lot of mesons, and then you put stringent limits. If I don't see any gammas transforming in a plus E minus pairs resonating to a certain date, and so on so far. I mean, a plus E minus collider, you have, as I mentioned before, a plus E minus that produce a gamma and an A prime, and then the A prime. Obviously, this may also decay in a plus E minus, but you can imagine in a collider how difficult it is. I mean, it's much easier to measure mu plus mu minus. There are also, practicalities practicalities means, let's say, the efficiency of your detection methodology, or the background you have could be suppressed. That is the reason why each lab focus on a specific reaction where they can be more, let's say, competitive in the measurement. So again, if you think about E plus E minus going in gamma, E plus E minus, you may, in a plus E minus collider, you have a lot of pairs, E plus E minus, coming from all possible, mechanism you may think about. While mu plus mu minus is a little bit more, easy to detect, very clean, and also less probable to be produced. So this is the reason why they focus on that. But again, you may think, very more complicated mechanism, monojets at LHC. There is, an entire section. I mean, we could talk hours about the search at LHC in this dark Higgs, dark vector, and also neutrino portal, because obviously having much energy, we are talking about TeV scale machine. You may also access, larger particles that have much higher masses. So you are sensitive to mediator that may have 100 GeV, okay? Or again, the same thing for Fermilab, we know, with the same technology that they use for neutrino production. This was the status in 2008, where you plot you plot the coupling I mentioned. This is epsilon, is the number, is the coupling that multiply the electron charge. You can always, you take two numbers and then you play with one of the two. Epsilon square is in some way proportional to the number of particles you produce, so the coupling to the square power, versus the mass of a possible A prime. And this was the situation in 2008. I will show you the same plot, how it is now, after, the people start thinking about it, was almost, fully covered. So in principle, you say, okay, This part, usually the gray area or the part that is colored means that this is excluded. So it means that all this, a cross section of 10 to the minus 6 for a mass of 10 to the minus 2, you know, this here is excluded. You cannot produce a particle with this combination of mass and cross section. But if I have a particle interacting at 10 to the minus 6 epsilon square with a mass of 10 to the minus 1, this is perfectly allowed. Okay, so the goal, in case you run an experiment seeking for dark matter and you don't see anything, the goal is then to try to extend this exclusion area and say that this part of parameter space is incompatible with the existence of dark matter. Okay. Another thing is that this is more about the kinematics. So let's assume that I throw my beam on a thick target where there is a conversion, the electrons produce gamma, gammas produce gamma prime. And then gamma prime, you know, first of all, should exit from the target. Second, should decay, this is my detector, should decay, I mean, within the volume of my detector. If the coupling is too weak, means that it goes away, fly away, and I don't see my detector. If I'm looking for, let's say, plasma, I'm assuming that I'm looking for an A prime decaying plasma minus. I need to have a combination of the coupling that shouldn't be too strong, because if it is too strong, all A prime decays within the thick target where I'm producing the particle. If it is too weak, it decays outside the volume, and then in both cases, I cannot detect. Okay? So it means that my exclusion limit, if I don't see anything, will have a shape like that, you see? A triangular shape with here decay into the shield, and so I cannot see it, or I see the rate too small or decay too far, and then I cannot see it again. And so this justify will see, you know, exclusion limits that for this beam dump experiment have such a triangular shape, or, you know, kind of area where there is only sensitivity. So your combination, depending on specific parameter of your detector, the energy of the beam, and the way how you're measuring the thickness of your dump. Okay, makes sense? And then we come to Jefferson Lab, where I guess in these days you learn about it. I just want to stress here that why this is, you know, a good place to do it. First of all, because the energy is such, I mean, 10 GeV electron beam is such that in principle you can produce particles that can explore. I mean, again, this kind of intuitive reasoning, but makes sense that you go in a range of 1 MeV to 1 GeV particle produced. All mesons we are producing sits more or less in that range, and we produce, you know, a reasonable amount of states here at Jefferson Lab. Okay, so energy is, you know, reasonable. Maybe, you know, that the dark matter sits in the range of 11 GeV, and then we'll never see a J-Lab. Very possible. Okay. But if it stay between 1 MeV to 1 GeV, this is a good range we can explore. And the second point is about the intensity, because we are saying that, you know, these particles are weakly interacting with the standard model particle. So we need to inject a lot of electrons that produce a lot of gammas to be sensitive, I mean, to explore a parameter space that makes sense. So we need to have a very high intense beam. And if you look at the intensity of Jefferson Lab with respect to, you know, all the other facilities, this is, you know, one of the best, probably, you know, the highest, one of the highest, let's say. There will be other facility like mines. I will go later on that, but the energy is lower. So again, this is perfectly fine if you are looking for your dark matter not in the range between 1 MeV to 1 GeV, but you focus in the range maybe between 0.1 MeV to 1 MeV. So in, you know, different areas. So let's take now one example. There was the first experiment that ran here at Jefferson Lab. It was called APEX, A prime experiment. See the fantasy of the name. Electrons, a thin target, so you radiate gammas. This is again high Z target. You radiate gammas, and one of the gamma is producing an A prime. And the A prime decays in E plus E minus, okay? Then what you need to do is just to measure through the septum magnets, because the problem is that this A prime is getting the boost from the electron beam, and so it's going to be focused in the forward direction. And you need to separate E plus E minus, and you cannot, I don't know if you had the chance to see the big spectrometers we have in Olay. This is, huge monster magnets that cannot be closer than something. So you need to put something in between, another, smaller one that just give a kick, as a magnetic kick to the particles, and then they enter in the acceptance of the spectrometer that sits at a larger angle. It's just a trick, okay? But the point is, you at the end of the day, you are trying to measure E plus E minus pairs. Obviously, E plus E minus pairs are produced by electromagnetic interaction, a lot of Battaglieri and other processes that we know very well, because we are studying mainly these kind of processes. In this case, these processes are a background for this measurement. But at the end of the day, you are just measuring E plus, E minus, trying to combine them in the invariant mass and look for a bump in this E plus, E minus. And depending on the characteristics of the beam, characteristics of your spectrometer, of your measurement, this define a range of masses that you can explore. So you will have, in this case, for that specific combination of parameters, you will have the maximum sensitivity to a possible particles that sits. These are the number of events as a function of the mass of E plus E minus pairs, that, as you see, there is no bump. I mean, there is a continuum that makes, there is no A prime here. Or if there is an A prime signal, it's fully deep under the background. There's the two options, okay? Either it doesn't exist, and so obviously we don't see any bump over it, or simply the background you have is too high, and then it covers, because the background fluctuates. There's a square root of number of counts. So within these numbers, you cannot say anything. You may have, a local fluctuation, but cannot say that I see a new peak. It's all clear. This point is clear. So I'm expecting to see, a bump over the background, as for any, peak, any resonance-like search. And you see there is nothing, and it is allowed to experiment apex to place an upper limit, that is this red curve here, that shows the maximum sensitivity here, and cover only a small fraction of this parameter space. So if you have an E plus E minus, assuming that your A prime is 260 MeV, you don't have any acceptance for it. You don't have any sensitivity. So again, the point is that putting together experiment from the world, that this is done, A prime is done at JLab. We had, A prime was done at Mainz, Apex at JLab, NA48 at CERN, Chloe in Frascati, you have Hades in Jülich, Phoenix in Brookhaven, Chloe again in Frascati, Babar, Slack, putting together all these experiments that the different beams energy, different acceptance for the detector, you can exclude, you can cover a significant fraction of this experimental area, just measuring E plus E minus pairs. Okay, and then this is kind of, the result. So far, I will, will show you an updated plot. HPS, it is another experiment running at JLab. It's not fully, it's partially run. There will be another probably next year, and another shot. Again, you have exactly the same concept. You are looking for visible decay of A prime produced by electron beam hitting a tungsten radiator. Tungsten high Z produce a lot of gammas, gammas decays, and most part of your E plus E minus are produced by radiative, effects. So give you a continuum, a spectrum that doesn't have any peak, because you produce, whatever energy, and gammas is zero mass. So you are not expecting to see any peak. You're just expecting to see, a continuum. And first of all, notice here the mass range covered by this experiment. It was running hole B, while the previous one was running on hole A, with different, different acceptance of the detector, different concepts of the detector. In this case, you are covering a range that goes from 20 MeV, let's say, to 100 MeV, so lower part. And again, you put your, upper limit in a region different, okay? That is exactly this region here. You see apex is here and HPS is here. On top of that, HPS had the clever idea to not only look at the bump hunting, so just taking a plus and minus, building the invariant mass and see if you have a peak, but also looking at detached vertices. Again, with the idea that if you are producing a weakly interacting particle, this is not going to decay within the target. It may fly for a while, and how much it flies will determine, again, the acceptance of your detector will be sensitive, obviously, only on a certain range of flying path for your weakly interacting particle that decay outside. The advantage is that as soon as you exit from the target, all these radioactive radiation effects gets depressed significantly, because the most part of radiation, E plus, E minus, you produce are within the target. As soon as you are, few centimeters outside the target, you are not expecting to produce any E plus, E minus pairs. So you beat the background. There is almost no background, and this is demonstrated. You see, for instance, when this is the background, how much radiation you have as a function of the distance from the vertex. All electromagnetic background is produced within the target. If I stay 4 centimeters out of the target, I'm expecting, much is it, 5 orders of magnitude less background. Or there will be, a little bit, but 5 orders of magnitude less. And again, since the trick here is to play between background and signal, you have an enhanced sensitivity for your signal. Even, you can explore a region that is very, very hard to reach if I have to beat the background, because if I increase my intensity, my electron intensity, is going to also increase the background. And then, again, is a game between the two. And that is allowed to, using this vertexing, that means I want to see a bump produced outside the target area, combining the two things. HPS is able to cover a region that is very, very difficult to reach just by brute force, increasing the number of, the time of your experiment in a standard bump hunting approach. Simply because you gain sensitivity by the fact that your background is lower, you have less variation of your background, so you have increased your sensitivity of your possible peak over a smooth background. Okay? This is an experiment that's still running at JL. And then we come to another, I'm introducing this X17 because it's the only claim of a possible light dark matter particle produced in an experiment, and nothing to do with us, because this was made by Atomic Institute in Hungary with a proton beam over lithium nucleus. You produce a beryllium excited states that de-excite emitting gammas. And these gammas, normally you're expecting these gamma sometimes convert in a plus and minus. And again, you measure a plus and minus, okay? So standard nuclear physics, really, really, basic nuclear physics. Few MeV proton beam, very low energy, tens of MeV. But if you have a particle produced the way, while the nucleus is decaying, producing gammas, you may have some of these gamma, again, that couple to a possible A prime. Then the plus and minus I'm measuring, they will reflect the fact that production goes through a resonance. That means I'm expecting a peak in some way, in some places. Where I'm expecting, if you look at the angular distribution of the two gammas, if they are produced by, let's say, a nuclear process where you have gammas, of all possible energies, this is going to be, something smooth with no peaks. But if you have a resonance in between, if I plug in a well-defined mass for X, you get, a sharp peak. So the E plus E minus distance in angle tells me exactly what is the mass. I mean, is correlated, strongly correlated to the presence of a resonance, and also I can infer from this, where I found this peak in this theta, I can also infer what is the mass of the X. And this was the measurement they did, found here is the first published paper. They were expecting, you know, in the E plus E minus, the angle between the E plus E minus, they were expecting something smooth. But at a certain value, they see a 7 sigma deviation. So there was a bump. Obviously, I mean, you can think that there may be, you know, billions of different nuclear effects that justify the bumps. Actually, people, I mean, experts in low energy nuclear physics did the calculation, and they didn't find any good reason why you should expect a bump there. So despite, again, you know, this low energy nuclear physics is pretty well known. So there is no a trivial explanation for that. And if you look at this is, you know, a very precise 140 degrees, and then if you plug in your stuff, here, 140 degrees on beryllium means this is for an hypothetical 18.8 MeV particles that you are expecting to see a peak exactly at 140. That, you see, is the one that they see. So from this measurement, they infer that there was a new particle, maybe nothing to do with the dark matter, okay? But anyway, they claim there is a peak in the E plus E minus pairs at these masses. Okay, unfortunately, MEG experiment measuring at PSI in Switzerland was measuring the muon to electron gamma transition, the precise measurement. They were also able, I mean, they have a proton beam, they shoot the proton beam on the target, and so they change a little bit the apparatus and they measure E plus E minus pairs and did exactly the same, you know, plot invariant mass, and they cover exactly a mass. Remember what HPS has a sensitivity that starts at 20, 25 MeV. So even if you have a particle in the range of 18 MeV, 17 MeV, this is outside the acceptance of the detector. Even worse for a apex that started from 180 MeV. So we are, you know, far away. So we never spot a possible X17 particle. So you really need to have, you know, the right combination of beam and detector. And this was, you know, likely. MEG had MEG2 arrangement. They change a little bit stuff. They shoot their proton beam on a lithium target, and they measure the plus E minus, and they didn't find anything. They didn't find any excess, and actually they exclude. This was, you know, the consistency. This was the equivalent of the mass of the atom key measurement compared to the region that they exclude. And you see that in principle, they excluded the region where atom key measures something. So this, you know, motivated a lot of effort. In particular, here at Jefferson Lab, there is an experiment running now, these days, in Hall B, to look for the X17 that was optimized with a different apparatus, was optimized to look for a possible signal between, let's say, 5 to 20 MeV, because we are expecting to see something in between, let's say, 15 to 20 MeV. So this was, you know, really matched with exactly the same idea. You shoot your electron beam. In this case, it's not a tungsten, is a tantalum thin target, and then you produce E plus E minus. You have, you know, a pairs of multi-wire drift chambers or, you know, gems to measure the angle. You have a spectrometer, a small spectrometer, and then you have a calorimeter, so you can measure the momentum of your E plus E minus pairs, and then you can infer the mass, the combination of the two. And this is the reach of X17 that is expected at the end of this term, you know, next month, actually starting in a week the experiment, because now the same setup is used to measure the radius of the proton, but with exactly the same setup. I mean, little changes can be optimized to cover this area. And you see that in principle, it will cover exactly the region that we are interested in to to confirm or disprove the existence of this resonant in plus-minus pairs at 17 MeV. And again, I want just to warn you that even measuring something at 17 MeV doesn't mean that we spotted the dark matter, doesn't mean that this is the dark matter coming from the sky. Anyway, it will be, a discovery, because we are not expecting to see any resonance in a plus-minus at 17 MeV. So it would be anyway, a very interesting effect. Another way to look at the same thing in colliders is gamma in A prime. A prime, I already mentioned, a plus and minus. This is just to give you an idea, looking at the different, best trees, a collider in China. Bell is a collider in a plus and minus collider in Japan. Babar was a collider at SLAC. LHCb had decays from B mesons in a plus and minus pair. So, I mean, you can play tricks, and each of these experiments produce, an exclusion with an exclusion limits, and this is the status where we are today in the visible decay. So remember, I showed you at the beginning this plot that was empty. Now, after how much, 18 years, people, look at back the data already collected, reinterpreted, recasted in this view or in these variables, or run the experiment specifically to exclude the region. And this is, where we sit now. It's, fully or significantly excluded. So the area, again, there are regions where you may still have a possible signal, but the area that is covered is strongly suppressed. And again, I want to let you notice, this triangular shape of beam dump experiment that has an effect also in this plot, because you can produce particles even in a thick target. We're mainly discussing thin target, but in principle, you can also do in thick target, and again, combination of shielding and detection area, detection volume will provide the sensitivity. Now let's move to invisible. So this was the visible. So we're assuming that you have an A prime that decay plus and minus. But for any reason, the mass of the A prime doesn't couple doesn't couple so strongly to E plus and minus, or couple in a weird way. And then A prime is such that decay mainly because again, here you have to have an epsilon. Coupling A prime to E plus and minus is not, let's say, natural. While A prime decay in K plus, in a K, an anti-K, probably, makes easier, more sense. You are expecting that the coupling can be larger. So invisible decay can be proved by, again, a plethora of different approaches. One that is very nice, because it's completely, let's say, doesn't require many assumptions, is the one that was proposed originally at VEP, so in Russia, and then at Cornell. And at the end, it was realized that at Frascati, and was proposed to JLab. This takes advantage of annihilation of E plus E minus in a fixed target experiment. E plus E minus, gamma, and the other gamma is replaced by something else. Either you see what this something else is decaying to, or you just take the gamma, measure the gamma, and tag with the gamma, since you know everything about E plus E minus interacting. You know the gamma, and so you can infer the missing particle that you're producing. Okay, this is smart because you don't need to make any hypothesis on how the A prime decays. This is in kind of, invisible, because it can decay in dark matter particles. You don't care. You only infer the existence of the A prime looking at the gamma that, is measurable. The problem is that, again, you need to have a good precision. You need to have good acceptance for this gamma and distinguish the gamma that is produced associated to a possible A prime, hypothetical A prime, with gammas produced with, all the radiation you have in annihilation process that is, huge electromagnetic background. So this is the problem. But anyway, so the experiment requires a positron beam. And again, Frascati in Italy had this positron beam. So they shoot it at this 500 MeV, so they can prove only as small part of, low masses area of the parameter space, but they did it. There was a proposal also for JLab for the future, as soon as a positron beam will be available here. The idea is to cover, with a very high sensitivity, because the intensity of the beam produced at JLab will be much higher than any other. The disadvantage of this technique, if you make the calculation, is that to have a sensitivity, which mass area you can cover. This depends on the positron beam energy, and it goes like the square root of the energy of the beam. So it means that with the 1 GeV, you cover an area up to 30 MeV. With 5 GeV, you cover an area up to 70 MeV. With a significant size. So it means that, this technique is applicable, but requires a very high energy beam if you want to extend the possible masses of this particle that you are producing, A prime, and high intensity and high energy that usually, are not, it's difficult to have them together. This is just with the E+, but with the E+, you can also look at the same experiment. E+ annihilate on E- in the material, in the thin target. And in this case, you may also look at the decay of E prime, again, in the visible mode, E+, E-. And this is what Frascati did, similar to what I showed you before for the X17 experiment here at JLab. And this is the way actually it is running now in this mode. So the experiment was optimized not for the invisible decay, but for the visible decay. And this is what the results they obtain. It seems that there is, a kind of variation, a kind of fluctuation of a couple of sigmas. So not enough to claim a discovery, but was more, inclined to confirm the atomic results rather than the MEG result. But they are still keeping data. So this we'll see, maybe in the next 6 months, what will be the outcome of this analysis. The same E+, E- with a single gamma measured was applied at Babar, and the same at Bell, and this was the exclusion limit. Why? You think, this is trivial. You measure a gamma and you infer from the gamma, you measure what is the missing particle produced. The problem is that usually colliders, at least in the past, Babar, didn't have a trigger, and the trigger was never meant to measure a single gamma, because again, you can imagine in a plus-minus interaction, you have an incredible amount of data with a single gamma. So you need to have much more selective triggers. And so they cut at the very beginning, any possibility to measuring just the gamma. They took only a couple of runs with this, let's say, open unbiased trigger with a single gamma that provided this nice, exclusion limit some years ago, because this was published in 2017. Bell was optimized, the new run of Bell 2 in Japan, that is an asymmetric collider similar to Babar, was optimized. They did on purpose to have the 2 gamma, a trigger on a single gamma, but was, tricky with all the technology that they had nowadays with respect. Babar was, an experiment running 20, 30 years ago. So, also the data acquisition was much more, let's say, despite the fact that Babar had, an incredible, nice data set, incredible, very, did a lot of precision physics very well. BDX experiment is another experiment proposed here at Jefferson Lab. Again, here the idea is beam dump. You throw your high intensity electron beam on a dump, or you produce a lot of particles, standard model particle, and you put a shielding in front of it, as usual, as a beam dump, and you have a far away downstream a detector that is sensitive to a possible interaction. The way you produce dark matter here is the same way you detect the dark matter into the detector. So this is kind of, bad, because you have to produce and detect. That means that your coupling goes to the 4th power of epsilon. So this experiment is strongly limited by the intensity, because when you see the number of events you are expecting, epsilon, remember, is smaller than 1. So epsilon to the fourth is, you are killing mainly the possibility of looking at something. So you really have to have a huge flux, a huge number of electrons thrown to the target. That actually happens at JLab because we have an experiment running soon called Muller, where they, throwing on the detector order of 10 to the 21 electron target in a couple of years of running. That is a huge number, I mean, a huge charge. So with this number, you can say something. What's the advantage of this experiment? Because it's trivial, because you're expecting to see in your detector some, appearance of energy that shouldn't be there. So it's not a disappearance. Disappearance is always tricky because you never know if you are not seeing something because you don't have under control the efficiency of your detector. But if you see 100 of MeV energy deposited into the detector, clearly, this is something new, something unexpected. Or is the neutrino interaction, because you obviously at JLab in the dump, you may also produce neutrino. Few of them, I mean, you are producing quite a number of neutrinos, but the problem is that only few of them will interact with the detector. But still, they will produce a kind of, appearance of energy from nothing. So the same technique, same thing applies to both dark matter and neutrino. But so it's going to be a background for this experiment. So if you look at, this is a, let's say, template for this beam dump experiment. Just focus on the one that we will run here at JLab. I mean, generally speaking, again, you have the beam dump, you produce, you have a shielding in front of the detector, and you only see a possible particle that is so weakly interacting with all the material you have in front that at the end give you a significant, sizable signal within the detector. And obviously you have not only to spot the signal, but you have the background. And there are mainly two sources of background. One coming from the beam. You have muons, for instance, produced in the beam. And these muons propagate far away from the production vertex. And, they are difficult to shield. I mean, they interact weakly, let's say, or not strongly. Or you have neutrinos. Neutrinos, you produce them and they do not interact mainly. So this is a chance at some point they interact with your detector. And this can be, again, one of the beam-related background. But you also have cosmic, because this kind of experiment is not like the one that look for direct detection that sits, under thousands of meters of rocks. This is done, in the accelerator environment, a few meters down in the ground. So you are exposed to all cosmic rays that obviously, they have a different topology because you are expecting a signal coming from the beam, while here you have mainly particles coming from the sky perpendicular to the detector. But when we are talking about a rate, I mean, we are expecting to see nothing in a 2 years' time. And if you think that, we have 1 muon per square centimeter per minute, the standard cosmic ray flux, you may, enter in the problem of having so many hits that you don't want, that, I mean, at the end, you don't understand. Even if you have a good interaction, you are completely covered by the background. So the experiment needs to, work in parallel to try to optimize the signal, putting the threshold as low as possible to detect a small energy transfer provided by your dark matter. But on the other hand, you want to beat the background, like, for instance, having some vetoes all around that at least the charged particle can exclude, cosmic muons. Again, think about what is a good efficiency for a plastic scintillator, 99.9%. Okay, I reject the cosmics, a charged particle at 99.9 means that I have 1 per mil. Now, if you have a billions of muons, even a 1 per mil inefficiency reflects in 1,000 or 100,000 of hits in your detector. And then you are comparing with some heat coming from the beam. So again, this is pretty tricky. Concept is simple, but in practice, this is more tricky than well. Then I mean, you can think about double layers, make things in order to multiply this 1 per mil by another 1 per mil, and then decrease by 3 orders of magnitude your inefficiency. So this is at the end, you know, the sketch of the experiment that is expected to run together with Muller in a parasitic mode, because Muller will get the electron beam, and the electron beam will be dumped on the beam dump of hole A, and we will place, you know, the detector in a dedicated facility that will be built in front, I mean, downstream of hole A beam dump. And the detector, again, is simple, you know, calorimeter based on crystals that put a lot of massive material together, you know, volume equivalent about a cubic meter. So it's 1,000 of crystals to about 3,000, 1,500 crystals. Fortunately, they are, you know, the repurposed crystals, because if you have to build a detector like that, I mean, with brand new crystals, this is going to cost about 10 million, just to have an idea. So it's really, really costly, but fortunately, there are many calorimeters dismissed by experiment running in all the world. So they were recovered from Be Good experiment in Bonn, in Germany, other from the Panda experiment that never ran at Fair, again in Germany, and other crystals will be taken from PRAD, actually the experiment running now in hole B. So I mean, just a reassembly crystals in the right shape. And you see that, for instance, for this experiment, is going to cover, again, remember the 3 targets, the 3 relic targets, with the different definition, different, let's say, details of the interaction, or more or less compressed. And this experiment is going to cover, you know, in the range between probably the range, let's say, 15, 20 MeV up to, 8, 10 MeV up to, let's say, 20, 30 MeV, is going to exclude the existence of this dark matter in that, you know, specific dark matter, if obviously, if nothing will be observed and will run for the time we are expecting. We are going to exclude so the existence of this thermal dark matter in that range. You see the difficulties. I mean, every time that you to change the kinematics and, you know, going down and going up, you really need to change a lab, change experiment, change the technology. NA64 is another experiment running at CERN with 100 GeV electron beam that runs, you know, in a similar way, is a little bit different, but in beam dump mode, exactly as similar to what I described for JLab. You see has a kind of, you know, maximum sensitivity to higher energy, because you start with a high energy beam, and for the future, they are expecting to cover this area. So, I mean, putting together, again, different experiments running in different facilities, you may cover and exclude the entire parameter space. Actually, an experiment like BDX was already, actually ran already at JLab. It was, you know, a pilot experiment with 1% of the volume that took data in 2 years, and put a limit that was, you know, within exclusion area already excluded by other experiment, but just demonstrated even with, you know, small scale experiment with a small volume, could run for a year time without any, you know, issue with the background, etc., demonstrating that, you know, the technology. And MESET mines that is proposed for the future will continue the exclusion to the lower masses area. MESA will be an accelerator that will be operational in mines soon. They are building it. This is a ERL, is energy recovery LINAC, or, you know, accelerator. Is a technique that actually reuse the same beam multiple times. So use part of the energy accumulating into the beam to give energy to the beam itself. So, I mean, you can keep a very high intensity and keep the beam for a while, or for a long while. It is a technique that was also used here at JLab with the LERF, that now has been dismissed and probably will be recovered again. This experiment, so will run up to 155 MeV, so very low energy, where you are not, you are below the production of pions, so you cannot produce neutrinos. So the kind of background you have here is completely different from what we have at JLab, where we start at 10 GeV, you produce for sure neutrinos. In this case, you don't. And it's also the way you measure a possible release of energy will be lower because you have less energy, you start with less energy. So it's, you know, different technique, different crystals, different option, but the same concept. And if you see, it's probably, you know, you remind the previous plot, this is covering a similar shape, you know, in the exclusion region of this thermic, of a thermal relic dark matter in the range now that sits in the range of, you know, few MeV or few tenths of MeV. This is the idea. Okay, so again, different facility with different energy beam, different detectors will do the same measurement, covering the same, similarly to what already happened for E plus E minus measurement that is a collection of different experiments in the same plot. Actually, this kind of beam dump were already run a long time ago at SLAC, was E137 in 1988, and then milli-charge experiment 10 years later. And because, I mean, the idea is simple. You have your target, you throw your beam, and then in this case, they took advantage of a mountain in front of you. So you are not expecting to see anything in a detector placed downstream. And then they put, again, upper limit on your possible production of particles, if you know your efficiency. One thing that, you know, one caveat is that reinterpreting all data is tricky because this experiment ran, how much is 40 years ago. So you lost all knowledge, all people. It was not time of Claude or ChatGPT, where in principle you can, you know, teach and train an LLM to get to keep in some way alive the experience. You really to rely on person. Person unfortunately die after a while. They disappear. They go away. So it's very difficult to, you know, combine information, recasting. This was made at that time in the 88. Also, data were taken in a different way. For instance, very stupid things. What was the threshold of your detector? How was, you know, exact geometry to run simulation to check the efficiency? That is one of the things that enter in the evaluation of the upper limit. So this is just, you know, a caveat that the new generation of this experiment, beam dump or whatever, they will be optimized. They will be, you know, in some way modern experiment where you know exactly, you have all details under control, and you can, since they are made on purpose to measure a certain effect. And this is very similar to LSND. This is another experiment running in Los Alamos, again, long time ago, where just the same group that put, you know, some limit extracted from the non-observation, in this case, you produce by zero that decays, from the not observation of an A prime, the first, they had a completely wrong evaluation. The same group at some point come up with a different evaluation of the flux of pi zero, and then you see how, you know, this upper limit move by order of magnitude, you know, moving up and down depending on the analysis. This was made by the same group, so not, you know, they just realized that some hypotheses in recasting these limits for these variables were simply wrong. So again, new experiment, you know, makes sense. You want to be sure that what you are measuring and also the way you are measuring. Okay. Other experiment is exactly the same technology, beam dump. In this case, are experiment meant to measure neutrinos, mini boon at Fermilab. You have, you know, GeV beam shoot on a target, a beryllium target that produce a lot of mesons, meson decay, pi zero produce A prime, and then you can look for a possible A prime in your detector, your neutrino detector. Okay, so you just recast or you put your numbers, and again you get your sensitivity can be, you know, more or less competitive with other experiments, but again excluded. Nobody observed anything in this experiment. Or even coherent. Coherent is a very nice experiment where they spot made for a different purposes. This was the coherent scattering on nuclei from neutrinos. As a seventh effect. That was, you know, just the idea that you should have a kind of coherent scattering of a neutrino was for a long while around, but then They just made the first experiment just a few years ago at Oak Ridge. You need a very high intensity neutrino source, low energy, let's say low energy neutrinos, and then measure the effect of this scattering on nuclei. But again, you have, this similar to the other experiment, you can also recast this kind of experiment to exclude. You try to see if there is, an excess of energy deposited in your energy. You don't see it, and then you can put, knowing the fluxes, knowing the luminosity, you can put a limit on the cross section. And finally, this is the last, let's say, technology. I already anticipated is a missing energy or missing momentum. Is a kind of complementary to the damp. In the damp, you need to produce and detect the dark matter, so it goes like epsilon to the fourth. Obviously, more trivial and easier is just to produce the dark matter and see that there is a disappearance of something. This is better from the point of view of the charge you have to inject, because it goes only to the epsilon to the second power. Your sensitivity, the number of events you're expecting doesn't scale as epsilon to the fourth, as epsilon to the second power. But on the other hand, it's much more tricky because you have to be sure that you don't have other effects that have some part of the energy of the momentum lost for other reasons. Assume, for instance, an hyperon, a lambda. You produce a lambda in one point, and then lambda travels because it doesn't interact and decay in a different point. Or if you have a neutron, you boost a neutron, the neutron escape from your detector because it's not, you don't have an efficiency 100% of your neutrons, and then you may confuse some energy taken away by standard model particle to something that is intrinsic. I mean, is beyond the standard model, like a dark matter production. So it's tricky. It's tricky to do it. But people propose it. For instance, an A64 experiment at CERN was the one that already ran. In this case, it's 100 GeV with an active target. And this is, the energy that you collect in the calorimeter behind the downstream of your target, and in the electromagnetic calorimeter, you sum up the two of them, and you are expecting to see exactly the energy you injected. Okay? If you see less energy, there is a region here. If I see an event in this region where I miss a significant fraction of energy, it means that probably it produced something that fly away. That so was a weakly interacting because I didn't see it. And they didn't, spot anything, but they put a stringent limit again on the same plot. You see, they were almost covering one of the two possible relic targets using this technique of missing energy. LDMX will be the leading experiment at SLAC in the future. I mean, it's already funded by DOE, but will run in next years. Exactly the same idea. On top of missing energy, you also have a missing momentum that give you, more strength, more and other, information. If you can constrain not only that you are missing some energy, but I see also that I'm expecting a particle in a certain direction. I don't see it. Maybe I'm really producing something that fly away. This is the idea. And again, they show that they can cover, fully the thermal target. One thing for this kind of experiment, it's true that you need less particles, but on the other hand, you have to, while in a beam damp experiment, the rate on your experiment, your detector is very low, because you're expecting to not see almost anything other than background, and background will be reduced by your tricks. In this case, you have to measure interaction by interaction. Every electrons interacting with the target needs to be tagged, needs to be reconstructed, and you need to be sure that all the energy you started with is the energy that the final state has. So it means that if you want to reach a high number of electrons, you have to shoot a lot of electrons, quickly. Namely, you also have to be very quick in reconstructing your final state and be sure that you are not losing energy. And this is pose also technological problem, because when you are talking about shooting 1 electron per nanosecond, means that you have to be fast enough to exclude, or let's say you have to have the entire chain, the entire pipeline of your detection needs to be, follow such a high rhythm. So you have to be sure that you're able to master each interaction, reconstruct, and be sure every nanosecond. Nanosecond is 10 to the -9. So this experiment claim a sensitivity when you have a range of 10 to the 14. Sorry, I think this was 10 to the 16 electron on target. So 10 to the 16 here is 10 to the 7 second. So it means that you have to have, if you want to have the experiment running for a year and not for 100 years, it means that you have to be able to identify each nanosecond one interaction for a year-long time. That, again, it's demanding, it's very, very tricky. But this is an experiment that has been approved as LAC for the future. Or again, a variation on the same thing. This is annihilation on a fixed thick target, is a beam dump made by positron, again, proposed for the future here at Jefferson Lab when the positron beam will be available. Or even more exotic and weird stuff. You may think to produce muons because in the dump you have secondary beams produced, muons, neutrinos, neutrons, etc. You can take advantage of these muons and using the muons to probe a different interaction that, assuming that the dark matter is not coupling to electron, but is coupling only to muons. Why not? Okay, and then you can think about a missing momentum, but this time you do with the muon. Muon has the big advantage that they interact less than an electron. They do not produce a shower. I mean, the probability is very low. So being low, it's much easier to measure a missing momentum of a muon rather than a missing momentum of an electron. And this has been proposed to Jefferson Lab Hall D for the future at the KLF facility, where you take advantage of the electron beam is meant to produce a gamma beam, and the gamma is converted in a K long beam. But you can take advantage of the first step when the dump, actually it is a weird dump with a magnetic, you just scratch a surface of a tube where the electrons produce gammas, mainly radiate, but they all can also produce muons. So you take advantage of the muons producing these first things. While the gammas go straight, here you put a dipole, a magnet, and then you bend the muons in an area where you then instrument with two dipoles, just a tracker. You measure the muon coming in, you measure the muon coming out, and you see if there is any significant missing momentum. And then you will have a calorimeter behind, again, electromagnetic and hadronic, in order to be sure that if you are in an elastic interaction of the muon, you will be able to spot it, to spot the energy and the momentum lost in the other two detectors. Again, the technology is the same, just using muons. Okay, skip details, and sensitivity can be, very sensitive to that. Just want to conclude saying that, these studies that we did for the dark matter JLab brought us also to consider not only something more tangible, let's say, because what we consider background in a beam dump or in a dark matter experiment is real particle produced. We know that we are producing muons, we know that we are producing neutrinos, we know that we are producing neutrons in the dump. And so the question was, may we take advantage of this secondary? Are they actually, calling them secondary beam is maybe too much, but we are producing fluxes of muons, a lot of muons, a lot of neutrinos. Can we use them? Can we take advantage of them? Actually, we did a study using Fluka. And yes, we found that the number of muons, for instance, JLab, Hall A, during Mueller experiment, will produce the highest flux, 10 to the 6 muon per second, ever produced, in the entire world. If you could, in principle, take advantage of these muons, you can use them to run experiments similar to the experiment we are running using electrons. Same thing for neutrinos. Neutrinos are mainly produced by decay of pions to muon. You produce one neutrino, and then muon to electron produce a second neutrino. So they are, focus, you see here the spectrum. You have a huge number of neutrinos produced at low energy, between 10 few MeV up to 50 MeV. They call it a decay at rest. So they have a specific that may have a significant impact on a supernova, for instance, neutrino studies. That this is something that usually this range is not covered neither by reactors that produce neutrino nor by high energy experiment that produce neutrino at higher energy, like the Dune, etc. So this can be another opportunistic opportunity for JLab to produce a secondary beam and do physics with that. Similar also to neutron beams that obviously cannot compete with Oak Ridge. This spallation source was made to produce a huge flux of neutron, but the energy of Oak Ridge is limited to 800 MeV because this is the energy of the initial proton beam, while at JLab we can produce neutrons at the GeV scale. And this can be relevant, for instance, if you think about aerospace industry, or if you want to go to Mars, you need to be sure that your material are staying into neutron in a space that has the entire spectrum. They are not limited to 800 MeV. You will have neutrons at few GeV also. And so extending this range is unique opportunity here at Jefferson Lab. Okay, we study all these things in a workshop last year. This is just to say that this LiDAR matter business that seems to be kind of butterfly search or something that you invent, you do your experiment. I mean, BDX is an experiment that was proposed 2018 and didn't run yet, so it's almost 10 years. So we are, after that. Other experiments were running, and here is the list of experiments expected to run. I just want to point out, the timeline here goes for, for the next 20, 30 years in principle. So these experiments are, nice, sometimes, simple, the technology. Running the real experiment is tricky, obviously, and requires time. And also preparing the experiment, as soon as this happened to us too, that when we finally were, finalizing the experiment, BDX that is being done, the same group that proposed this idea that was from Slack, they say, come on, but this, being done to require to produce and detect. Why don't we invest in a missing experiment? And you say, come on, we already, invested 2-3 years, went in front of the PAC here, Program Advisory Committee at JLab 3 times to get the approval. And now you are telling me that we have to trash everything out because you have found a new ideas that is, maybe more performing, even more tricky. And then, we split. They decided to pursue it at Slack, where they were originally from. And we decided to move forward with BDX. This is just to explain that even if, many of these experiments are, let's say, simple, not conceptually complicated, anyway, they require a lot of effort, experimental effort. And even recycling crystals in a BDX experiment that is, very low profile experiment, will require millions of investment in terms of infrastructure, in terms of running the experiment, getting the electronics, etc., etc. So, simple, but on the other hand, anyway, costly. And I'm not talking about all the experimental planned at CERN, where the scale is, you think about JLab and you multiply by a factor of 100 at least, in terms of number of channels, number of, volumes, everything is scaled by 2 orders of magnitude. So it's, again, very, very tricky. For instance, there will be an experiment in the future called SHIP that is, a beam dump experiment, exactly the same what we want to do here, but the experiment will have 400 GeV proton beam. You can imagine the radiation that you produce when you shoot high intensity 400 GeV beam on a piece of material. They have to, I don't know, the beam dump environment is going to cost, hundreds of millions just to shield it, to avoid that people are killed by radiation, just for that. So again, this is very, bright, I'm done. Very bright field demonstrated by the number of possible experiments that, investment that experiment working, focus on that, or that are running for other purposes, but they also try to explore this dark sector. in a time scale, again, that span from now to 2040, so 20 years from now. So if you are interested in this kind of physics, I think it's a good time. With all the caveat, I try not to scare you, but just to explain the reality as it is, not to be too enthusiastic. I mean, I spent 10 years of my career after BDX experiment. So the first that invested on it can be, a nice place where you want to invest a part of your efforts because this is nice, it's simple, and, it's a fun anyway. So this is just a summary of what I say. Thank you very much for your attention. And now, questions. Curiosity, whatever.
List one, otherwise I don't let you out.
So when is the installation of BDX expected to take place?
We are expecting to have the pit built next summer, before the Mueller will really start. Yes, because it's not obvious to dig a hole. I mean, it's not going to be a huge hole, but anyway, it will be about 10 meters, 12 meters long, by a couple of meters you have to go down up to the beam height, so 8 meters down in the ground. And you know that we are under the water table here in Virginia. So every time that you dig after, a couple of meters, you will find water around. So, I mean, digging and making a kind of a swimming pool is not trivial. A couple of millions anyway.
Okay. So the goal is to be able to run this starting with run 1 of Mueller.
Yes, we hope. Otherwise, we'll take advantage of any interruption of the beam, because when they will dig, there will be, not for a long while, but at least when they will dig the hole, you have vibration and you cannot run the accelerator meanwhile. Right. So you need to take advantage of one of the set time when the accelerator is down, shut down.
Okay, thank you. Are there any planned, similar beam dump or, other sort of like opportunistic or like parasitic experiments planned for like the EIC?
For what?
For the EIC? Or
yes, there are a couple of them. So EIC is a collider, so it's a different concept. There is no beam that is dumped. Actually, there is a beam that sometimes is dumped because after the refilling, the beam is dumped on a dump. We are proposing a similar program using doing with the proton beam at. There will be, let's say, an injector called AGS. AGS, yes, I think it's AGS. It's part of the complex at the EIC that will have a proton beam, higher energy, 20 GeV, that will provide a similar physics proposed for SHIP. SHIP is, again, a proton beam, higher energy. This is a lower energy, but the same concept. We propose that we'll see, because we want to organize a seminar, it's a conference on that next year. We'll see if Brookhaven and will react positively. But yes, in principle, obviously, being a collider is not the same as having a fixed target or a program like here, where every time, the beam is dumped on the dump and that's it. And so you can take advantage of it.
I also want to ask, so we obviously have this huge wealth of the data that's already been taken with like JLab, Rick, everything like this, Slack, everything like this. Has there been any initiatives to go and go through some of the existing data and looking for any either invisible dark matter decays, so you just have like a missing the missing mass that might align with some of the heavy dark matter, like heavy photons or things like this, or even just photon or heavy photon or like axion to dilepton decay or something like that.
It will. I mean, yes. The brief answer is yes. There was some attempt. The problem is that, particularly JLab, We look at, for instance, within class and class 12, but the problem is the current is too low. So, okay, you can extract some upper limits, but they are well within the excluded region. So it doesn't make, much sense to invest time. I think that the JLab, the strategy that was chosen was more about proposing dedicated experiment. I mean, the advantage of having such an intensive, even Apex was an experiment running for a few days. Okay, you have to, arrange everything that makes the setup not trivial, but the number of days you really have to run, or Mueller will run anyway for a year time. So you don't need to have, it's easier in some sense to do a specific and optimized experiment rather than going through different story for colliders. Colliders runs usually, colliders run in always in the same way. So they really accumulate a huge statistics with the same experimental setup. And so you may have a good chance to look at, decays, for instance, or mesons like LACB did, putting, very stringent limits. Okay, come on, they run, I don't know, femtobarn luminosity in years. So obviously, they have a huge amount of pi zero produced, and then they can look at this conversion of gamma pi z, one of the two gamma of the decay in A prime. Here, JLab, you have different experiment running for weeks time, maybe, months, in conditions that are then different. For instance, in all B, we are running with target, on hydrogen, then we run target on deuteron, then we run an experiment on nuclei, and then we run with a different setup, and then we have the polarized target. So putting together all these pieces are, I'm not saying, it's costly in terms of resources. So at the end of the day, probably better think about, optimize configuration, and you propose it, and maybe in a week time, X17 will run for a week. It's a very short time. Obviously, you need to have, and this was a kind of spin-off of a PIRAD experiment, the radius measurement, where you use exactly the same equipment, maybe, and the trigger will be a little bit different, but the same concept, the same equipment, and you run for an extra week, and you get a reach that is, the best in the world, if the experiment will run as expected.
So as you talk about gravitational lensing, I just want to know, so how we can deviate that there's dark matter, so it's the gravitational lensing happens because of any cloud somewhere else. So how we differentiate with dark matter and any other?
Yeah, because I think that, no, I'm not an expert, but I think that the idea is, again, very simple. You associate the mass to the visible mass. So you can estimate how much light you're expecting from a galaxy. Sorry, what's the weight of a galaxy? Because you count the number of stars, so you see how bright that they are. And you associate, there is a relationship between how much light you see to the quantity of mass you're expecting. And then what you do is, based on that, you do your calculation. You're expecting that light gonna be deflected in a way that is incompatible with the light that you see. But again, this is not a few percent effect that you say maybe I'm underestimate the quantity of mass. We are talking about effects that are macroscopic. We are talking about that, again, 85% is not reconciled to observation of a mass of the universe. If you estimate it, you find 85% is dark. It's not light. It's not connected to the. There were other hypotheses that, for instance, about since a significant fraction of the mass of the universe is related to the dust. I mean, it's not concentrated. But again, I think that this cosmology is you have to trust in some way to these observations. I don't know how reliable they are. I mean, sometimes there is a significant change in the paradigm of a cosmology description of things. So I'm not 100% sure that they are, stringent limits that will be, cast in the stone. I'm not 100% sure, but let's say that there is a consistency to say that the most part of the fraction of mass that can be connected to the dust that doesn't produce light is incompatible with this 85%. I think this is, a solid statement. So there should be something else. Maybe not 85, maybe 50%, but half and half. Half you understand and half you don't understand is a lot.
Thank you for the talk. I just wanted to add, even cold hydrogen dust radiates at, the 21 centimeter line, so you can see it. So we know it's not that, at least.
Yeah, exactly. I mean, I think that there are, again, I'm not an expert, but let's say that there are for sure indirect observation and also, signals, things, let's say a phenomenology that in some way you can explain, you can reconcile. Again, my boss, my teacher told me that physics and astrophysics are different business because physics try to, or physics, let's say nuclear or high energy physics, try to focalize and in some way create the environment where you can do a clean measurement, a quantitative statement about what you are measuring. Cosmology and astrophysics is nice because you discover things, you can do observation, but doing observation is not the same thing that quantify it. So, and again, this is demonstrated by the fact that the model we have of the cosmos, but it's natural, I'm not blaming astrophysicists. I'm just saying that it's very difficult to extract or to guess from observation, an entire picture of a universe that, is an entire universe. Obviously, our goal is much more smaller in a very focused, very small stamp of possibilities. You explore them in a quantitative way. So it makes sense that we are, let's say, more precise, more quantitative understanding. But on the other hand, if you want to see, for instance, we observed now KM3net observed the particle with the highest energy, a neutrino with the highest energy of a particle produced. And then obviously this is, a nice observation, because you may ask yourself, what's the mechanism that accelerate particles up to hundreds of TeVs or PeVs, sorry, in the nature? What is the mechanism? So it's a good stimulus for understanding, but it doesn't mean, or it's very difficult to find a quantitative answer to that in cosmology. It's easier in our case where you focus on a specific effect or try to get rid of all the background, let's say, and focusing on a specific effect, and you measure it. That is the reason why I think that also this LiDAR matter search at accelerator is in some way justified, because it's, in my opinion, I think it will be, even if you observe, for instance, there was an experiment, the DAMA in Italy, under Gran Sasso Lab, where they observed an oscillation of the flux of the signal within some crystals. They claimed that the crystal were extra pure, was sodium iodide crystals made on purpose for this experiment, completely shielded under tons of rocks. And they saw a modulation, a seasonal modulation between winter and summer that they claim as a signal of the dark matter. Because you can imagine that when the Earth rotates around the sun, you have, in one case, assuming that the wind of WIMPs is coming from the same side, the same place, when you go in front of it, or when the Earth goes on the other side, you have a different speed, a different velocity. In one case, you are in front, in the other case, you are following the wind of WIMPs. And so they cast in a calculation, and they found that it was compatible with, in principle, with the dark matter observations. This was the only claim. Then two experiments remade the same measurement, one in Korea, the other in Australia, and they didn't find even the oscillation. But this is just to say that, even an observation in a detector doesn't automatically mean that you discover dark matter. Will require, multiple detection by different technologies, all pointing in the same direction. And again, this is not easy in astronomical observation.
So if in the next years this experiment will like this model, in which direction should we search? Like, how should we modify our model to search for dark matter, to search like for an explanation?
I think this is, you know, there will be millions of models well before we will exclude these ones. I don't think there will, you know, we are not missing fantasy again, because we are leaking completely. We don't have phenomenology. All these models, all these, you know, are based on, you wake up in the morning and say, okay, why, I mean, dark matter may interact in this way. Let's do a couple of, you know, back on the envelope calculation and see if it is compatible with the, you know, other observation, astrophysical. You see that, you know, this is not disrupting any other prediction, and that's it. So it's, you know, I'm not saying a day work, but, you know, a year time work for a theoretician to come up with a completely different hypothesis. While for us, it's not, you know, months time, is years, tens of years to run a single experiment to exclude. HPS2 was, you know, was approved 5, 6, 7 years ago at least, and it still needs to take part of the data. But all these experiments requires, you know, about 10 years to run. So I don't know, I mean, it's, again, I invested my time in it. So I'm leaving demonstration that I trusted. I mean, I had the feeling that worth spending time on this. But on the other hand, I'm also, this was a criticism by, I remember Bob McKeon at some point was, you know, the deputy director here at JLab, when we presented the first time, a long time ago, this idea. And we say, okay, we have, you know, the visible decay where you look at E plus E minus and say, okay, I mean, you measure the spectrum E plus E minus. Say, no, but in case we can also look at the invisible decay. And then you say, okay, but then you move from one parameter, the mass of the E prime, to, you know, 4 parameters model. It's too easy. I mean, for an experimentalist, it's really scary because you can, you know, you can do whatever. And then 4 is not enough. Yes, because you have a dark matter that when interact produce 2 states, and then you add another parameter that is how the splitting of these 2 states. Yes, but one of them is decaying away and the other in a different way, and you introduce other parameters. So where you are stopping? Are you trusting? Are you really, you know, investing your time in exploring all possibility? No, no way. So this is tricky. It's tricky. It requires, you know, I would say simple, try to be as simple as possible, and also in the concept of this experiment, as far as we can, because, I mean, at the end, again, each experiment requires time, but not to be, I think we need to keep, you know, the feet on the ground and be sure that you are not projecting, because these are ideas from a colleague of yours that can be, you know, a smart colleague. I'm not blaming, again, the theoreticians. I'm just saying that there is no evidence, no phenomenology that limit the fantasy of our colleagues. So I don't think that models, if we don't find something in a direction, there will be an explanation to explain why we didn't see there, and we need to look at it in a different direction. For instance, with this muon coupling or the experiment running with muon beams in particular, were originally meant for the G-2 anomaly of the muon. And so, you know, there was a big fuss because everybody say, okay, yes, maybe a dark matter, an A prime can be, you know, you are missing part of this correction that you are expecting, and this can reconcile the measurement to the other. And then, I mean, Brookhaven, Fermilab made the measurement of G-2 of the muon and demonstrated that, you know, it's the oscillation, even if there is a, you know, discrepancy, this is a completely a different scale, saying, okay, there is no anomaly mainly. And so, I mean, the theoreticians say, yeah, okay, but you know, this G-2 was not the real motive. I remember when I started 10 years ago, you know, first slide was, yeah, because, you know, with the A prime, you also reconcile the muon G-2. Now this slide was deleted by, you know, by the pool, because it's not anymore the case. So observation, I mean, again, this is just to say, something trivial and obvious. We are physicists, and physics is based on scientific method. Scientific method means you have an observation, you try to explain the observation. You're not trying to invent a possibility and then see if the observation is there, because it's too risky. I mean, it's too easy to completely go in a wrong direction. You need to anchor your things to phenomenology, to something that you measure. And then it's fine to have, interpretation, to have variation, but you have to start from observation.
Okay, maybe if there aren't any more questions, we should stop here.